In the late summer of 1944, a German anti-tank gunner, concealed in the thick hedgerows of Normandy, learned to trust the mathematics of his weapon. But as the weeks dragged on, a terrifying contradiction began to infect the German defensive lines. The contradiction usually revealed itself at dawn. By the final year of the conflict, a staggering percentage of German heavy armor was not defeated by Allied anti-tank fire. It was destroyed by its PT's own crews, simply because the logistical burden of moving dead weight had exceeded the capacity of the German army. They had built weapons so massive they became single-use assets the moment their engines failed. The German gunners, watching American Shermans burn in the distance, assumed the enemy was trapped in this exact same logistical nightmare. If the Wehrmacht could not pull its armor off the battlefield, surely the Americans were abandoning their own shattered vehicles in the mud. But the American armored doctrine was not built around artisan fortresses. It was built on a completely different philosophy of metal, mass, and time. When American ordnance engineers finalized the blueprints for the M4 Sherman, they did not attempt to build an impenetrable fortress. They knew that in a global, mechanized war, armor plate would eventually be defeated by a larger, faster projectile. Instead of trying to cheat the physics of ballistics, they engineered a machine to survive the mathematics of logistics. The Sherman was explicitly designed with the understanding that it would be shot, disabled, broken, and burned. It was not built to be invincible. It was built to be repaired. This philosophy was stamped directly into the steel of the hull. A German position that had successfully devastated an American armored spearhead on Tuesday would brace for a renewed assault on Wednesday. A close inspection of the Sherman reveals heavy steel loops welded to the front and rear corners of the armor. These were standardized lifting eyes. American designers knew that tanks would slide into deep craters, shatter their tracks on mines, and take catastrophic hits to their engines. From the very beginning of the production lines in Detroit, they integrated the exact anchor points required to lift a 30-ton vehicle out of the mud. The heavy German Panthers and Tigers were designed strictly to fight. The American Sherman was designed from its inception to be recovered. The internal architecture of the American tank was an exercise in modular simplicity. If a German anti-tank shell shattered the front drive sprocket and wrecked the transmission, the vehicle was not permanently dead. Mechanics could simply unbolt the massive rounded steel nose of the Sherman, slide the entire ruined transmission assembly out as a single heavy unit, and bolt a fresh one into place. There was no need for a master fitter to file down misaligned gears. A transmission built by Chrysler in January would slide perfectly into a hull welded by Fisher Body. They expected to face infantry, or perhaps a cautious, depleted remnant of the previous day's tank force, in March, and it could be installed using standard wrenches in a muddy French orchard in July. The suspension system followed the exact same brutal, interchangeable logic. Instead of the delicate, overlapping road wheels that routinely paralyzed German recovery efforts, the Sherman relied on self-contained suspension bogies bolted directly to the outside of the lower hull. If an exploding mine blew off a wheel, an American crew did not have to jack up the tank and dismantle an entire interlocking system. They unbolted the shattered bogie unit, dropped it in the dirt, and attached a new one. What took German crews half a day of exhausting, dangerous labor to fix could often be repaired by American mechanics in less than an hour. To the American military, a disabled tank was not a corpse. It was merely a collection of functional modules temporarily disrupted by a broken component. A pierced hull was just a hole that required a welded patch. A ruined engine was just a heavy block of metal waiting to be lifted out of the rear deck. By intentionally stripping away the artisan complexity, instead, Through the morning fog, the exact same number of Sherman tanks would appear on the ridgeline that plagued the German heavy armor. The United States turned battlefield damage from a fatal condition into a temporary delay. They transformed the tank into an interchangeable industrial appliance. But brilliant engineering alone cannot rescue 30 tons of dead metal under enemy fire. The standardized lifting eyes and interchangeable transmissions were entirely useless. If the disabled hull remained trapped in a contested hedgerow, a broken Sherman was easier to fix, but it still required a massive, coordinated application of force to drag it back behind friendly lines. The machine was built to be resurrected. The question was, who actually went out into the fire and the darkness to bring it back? The German gunners retreating from a battlefield assumed they were leaving behind a graveyard of dead steel. They did not realize that the moment the firing stopped and darkness fell, the American ordnance maintenance companies moved forward. These were not frontline combat infantry. They were highly specialized units of heavy mechanics, riggers, and armor welders, operating in a permanent state of exhaustion just a few miles behind the line of contact. Sometimes, through the optics of a trench periscope, a German defender could see raw, unpainted weld scars on the sloped armor of the approaching vehicles. To them, a battlefield littered with smoking Shermans was not a defeat. It was an industrial worksite. Their primary tool for this labor was a towering, utilitarian machine called the M32 Tank Recovery Vehicle. To solve the physics problem of moving 30 tons of dead weight, American engineers had simply taken the proven chassis of a Sherman tank, removed the main gun, and replaced it with a massive, fixed superstructure. Mounted to the front was a heavy steel A-frame crane. Housed inside the hull was a winch capable of pulling 60,000 pounds. Because the M32 was built on the exact same hull as the tanks it was designed to rescue, it carried the same armor and the same engine. It did not require paved roads or dry weather. It could drive directly into the exact same muddy crater, cross the same shattered bridge, and absorb the same mortar shrapnel as the combat tanks it was retrieving. When an American armored column left a mobility-killed Sherman in a ditch, the recovery protocol was immediate and standardized. Under the cover of night, an M32 would crawl up to the disabled hull. Mechanics would slide into the cold mud beneath the tracks, located exactly where their own anti-tank shells had punched through hours earlier. To the German infantryman and tank commander, feeling in the dark for the heavy lifting eyes welded to the armor, they attached thick steel cables. The M32 driver would engage the massive Gar wood winch. The internal gears would bite, and the cables would pull taut. Unlike the German Famo half-tracks, which required a desperate, synchronized train of multiple vehicles to drag a heavy tank, a single M32 could anchor itself in the dirt and winch a dead Sherman out of a deep trench by sheer mechanical force. Once the tank was dragged clear of the immediate kill zone, the American logistical network functioned like a massive, distributed hospital triage system. If the tank had thrown a track or shattered a suspension bogie, the ordnance crews often fixed it right there in the dark, working under heavy canvas tarps to hide their flashlights from enemy aircraft. If the damage was catastrophic, a ruined engine, a shattered transmission, or a cracked turret ring, the M32 towed the hull a few miles rearward to a maintenance park. These parks were sprawling, camouflaged factory floors hidden in French orchards and Belgian farm fields. The darkness there was broken by the sharp, brilliant blue flashes of arc welders patching entry holes in sloped armor. It felt as though they were fighting an immortal enemy. The tactical reality did not match the strategic result. Heavy cranes swung replacement engines through the air. The ordnance battalions carried vast mobile warehouses of interchangeable parts in heavy trucks. ensuring that a shattered transmission could be swapped out seamlessly. This was the hidden machinery the German defenders could not see. It was an industrialized recovery network, pushed directly to the edge of the front lines, treating disabled armor as a fully renewable resource. But a logistical blueprint is only theoretical until it is subjected to the violence of a major offensive. The question was not just whether the M32 and the ordnance crews could pull a tank from the mud. The question was how fast this system could operate against the relentless friction of a combat campaign, and what that speed did to the balance of power when the sun came up. To see how this logistical machinery dictated the reality of the battlefield, consider a typical evening in the Normandy bocage. As dusk settled over the hedgerows, two tanks sat immobilized in the mud, separated by only a few miles of contested terrain. Both had suffered identical tactical fates. An 88mm shell had shattered the front drive sprocket of an American Sherman. Germany was fielding weapons of undeniable mechanical superiority. The high-velocity guns of their Panthers and Tigers were mathematically tearing the American armored divisions apart, snapping its heavy steel track. A mile away, an American artillery fragment had wedged itself deeply between the overlapping road wheels of a German Panther, locking the suspension tight. Both machines were officially mobility killed. Inside the Panther, the German commander checked his watch in the dark. He radioed his battalion headquarters, requesting the heavy recovery train. The response was static, followed by a bleak reality. The FAMO half-tracks were engaged elsewhere, or they had been destroyed by Allied fighter bombers that afternoon. The Panther was too heavy for any other vehicle in the sector to pull. By midnight, knowing the American infantry would sweep the field at dawn, the commander accepted the inevitable. He ordered his men out, dropped a thermite grenade into the breech of the magnificent 75mm gun, and wired explosives to the engine block. In a bright, violent flash, 45 tons of irreplaceable German engineering was permanently erased from the war. Across the line, the American crew experienced a vastly different night. They did not abandon their shattered Sherman. They waited for the heavy, low rumble of the M32 recovery vehicle. Working under the faint glow of red lens flashlights, riggers secured the tow cables. The tank was dragged out of the kill zone and pulled into a camouflaged maintenance park, hidden in a nearby orchard. German High Command collected daily after-action reports filled with staggering kill counts, calculating that the Allied armored advance must surely grind to a halt. The ordnance mechanics did not need to file down custom parts or solve complex engineering puzzles. They worked with the brutal efficiency of an assembly line operating in reverse. A crane lifted the shattered drive assembly away. A replacement module, pulled directly from a supply truck, was bolted into place. Arc welders sealed a patch over a minor penetration hole. The tracks were reconnected and tensioned. By 4 in the morning, the tank was refueled, restocked with ammunition, and handed back to its crew. When the sun rose, the German anti-tank gunners looked through their trench periscopes and experienced the terrifying contradiction that defined the late war. The American platoon advanced out of the morning fog at full strength. The German defenders could see the fresh, unpainted weld scars on the very Sherman they had successfully stopped the day before. It felt like fighting a phantom army. The American forces seemed to possess an infinite supply of fresh tanks. In reality, they were often just fighting the exact same machines they had killed yesterday. This overnight resurrection completely inverted the mathematics of attrition. A single American Sherman might be disabled, recovered, repaired, and returned to combat 3 or 4 times in a single month. The German High Command was dutifully tallying these daily tactical victories, assuming each smoking hull represented a permanent subtraction. Under the weight of such unsustainable losses, yet the American presence only thickened. To the German military mind, The definition of a destroyed tank was becoming increasingly absolute from the Allied inventory. They did not understand that they were fighting a war of absolute losses, while the Americans were fighting a war of temporary delays. This tactical disparity reset the board every single morning. An army that can retrieve and repair its wounded machines overnight will inevitably crush an army that must burn its own stranded armor. The local miracles performed in muddy French orchards were already deciding the fate of individual battles. The only remaining question was how this daily mechanical advantage scaled up into a strategic hemorrhage that would eventually consume the entire German armored force. What happened in one muddy orchard in Normandy was happening simultaneously across hundreds of miles of the European front. The overnight resurrection of a single Sherman was a tactical annoyance to a German gunner, but multiplied by thousands of vehicles across an entire theater of operations, it became a strategic avalanche. The American logistical network effectively severed the link between taking battlefield casualties and losing combat power. An American armored division could suffer severe vehicle casualties during a week of brutal hedgerow fighting. According to traditional military arithmetic, that division should be rendered combat ineffective, requiring a halt to wait for replacement tanks shipped across the Atlantic Ocean. Instead, because maintenance companies were operating directly behind the line of contact, dragging shattered hulls out of craters and patching them with interchangeable modules, the 75mm armor-piercing shell of a Parquet 40 anti-tank gun left no room for ambiguity. When fired from a camouflaged ambush position, if a vehicle lost a track, shattered a drive sprocket, or suffered a minor engine fire, it was a mobility kill. That same division could maintain an operational readiness rate of 80 or 90%. The United States military had essentially built a distributed, mobile automotive factory across the fields of France. A repaired Sherman, already driving toward the front line, was vastly more valuable than a brand new tank sitting on a cargo ship in New York Harbor. On the opposite side of the line, the German reliance on heavy, bespoke armor created a strategic hemorrhage that no factory could outpace. The German Ministry of Armaments in Berlin was constantly tracking production numbers, celebrating when the output of Panthers and Tigers peaked in the summer of 1944. But those production figures were a paper illusion. The critical metric in mechanized warfare is not how many tanks roll off an assembly line. It is how many tanks can actually start their engines and cross the line of departure on the morning of an attack. Because the German military could not reliably recover its heavy armor under combat conditions, every tactical retreat became an operational catastrophe. When the Allied armies broke out of the Normandy bridgehead and forced the German defenders into a rapid withdrawal, the roads became a graveyard of pristine German engineering. A panzer division might begin a retreat with 40 operational heavy tanks. If 10 of them broke down with shattered final drives and 5 simply ran out. In the retreating reality of the Wehrmacht, a mobility kill was a death sentence. Without the immediate capacity to drag a heavily armored machine of fuel, they could not be towed. The heavy FAMO recovery trains were either too slow, bogged down in the mud, or already destroyed by Allied fighter bombers. The crews had no choice but to plant explosive charges and walk away. The American army did not have to shoot every German tank to destroy the division. They only had to force the Germans to move backward, faster than their overtaxed recovery vehicles could operate. The German heavy tank program was ultimately defeated by its own physical mass. The designers had built vehicles meant to dominate a specific, static slice of terrain, completely ignoring the logistical reality that armies must move, supply, and recover their equipment under relentless friction. They built 56-ton fortresses and then watched helplessly as those fortresses were swallowed by the earth, abandoned by their crews, and blown apart from the inside. The failure of the German heavy armor and the triumph of the American recovery system forces a complete re-evaluation of military machinery. The German anti-tank gunner who calculated victory through kill counts was blinding himself to the most powerful force on the battlefield. The outcome of the mechanized war was not determined by the thickness of a steel plate or the velocity of an armor-piercing shell. Out of the line of fire, that tank had to be abandoned, usually blown apart from the inside by its own crew to prevent capture. Which raises a profound historical question. If the ability to survive a direct hit is not the most important quality of a fighting vehicle, what is the true measure of a tank's value in a total war? The German anti-tank gunner hiding in the Normandy hedgerow was not wrong about the lethal capability of his weapon. When his 75mm shell struck an American Sherman, the tank broke exactly as the physics of the strike dictated. His calculation only failed because he believed that the violence of the impact was the final word. He thought the war of attrition was being fought purely between the muzzle of his gun and the armor of the enemy tank. He could not comprehend that the true battle was being waged between his own static, fragile logistics and an American industrial system that refused to accept a disabled machine as a dead one. The true measure of a tank in a total war is not its ability to survive an ambush unscathed. It is its capacity to absorb catastrophic friction and return to the line of departure. The German military designed weapons for a pristine, theoretical battlefield. Therefore, when a German gunner saw an American Sherman throw a track or vent smoke from a ruptured line, he logically assumed the American tank, where mass and armor were supreme. The Panther and the Tiger were artisan monuments to engineering arrogance. They were breathtakingly lethal when their engines ran, but the moment they broke down, they became 56-ton anchors that dragged their own retreating army into the earth. The German reliance on these heavy machines ultimately resulted in their own crews blowing them apart from the inside, defeated not by American firepower, but by the inescapable weight of their own design. The American Sherman was born from a completely different philosophy. It was built with the profound industrial humility to accept that it would be pierced, burned, and shattered. Its greatness lay not in its armor plate, but in its standardized lifting eyes, its interchangeable modules, and the heavy recovery vehicles, designed specifically to drag it out of the mud. But a logistical system is not just machinery. It is a continuous chain of human labor. The immortal American armored force was not created by a magic factory in Detroit. It was forged in the freezing rain of French orchards and Belgian farmyards by the men of the ordnance maintenance companies. These were the mechanics, the riggers, and the armor welders who never painted victory rings on a gun barrel, shared the exact same fatal diagnosis. They were projecting their own logistical paralysis onto their enemy. The German troops were not wrong about the physical. They were the men who crawled into the cold mud beneath 30 tons of unstable, shattered steel in the dark, feeling blindly for the towing points. While enemy artillery shells fell in the next field, they worked in a permanent state of exhaustion, their uniforms coated in thick black grease and hydraulic fluid. They used heavy blowtorches to cut away jagged, ruined armor plate that was often still stained with the blood of the previous crew. They operated massive cranes in the dead of night, trusting their lives to the tension of thick steel cables. They were an invisible army of blue-collar labor, fighting a relentless war against gravity and broken metal. When the dawn broke and the German defenders looked through the morning fog, terrified by the sight of the exact same Sherman tanks rolling over the ridgeline once again, they were not witnessing a miracle of American armor. They were witnessing the overnight labor of thousands of unnamed mechanics. The outcome of the mechanized war had already been decided in the dark, secured by the sharp spark of an arc welder, the heavy turn of a socket wrench, and a fresh steel patch welded firmly over yesterday's fatal wound. Vulnerability of the Sherman. But what they could not see was the shadow machinery operating just behind the tree line. They assumed that a disabled tank marked the final act of a combat sequence. They did not realize that the moment an American crew bailed out of a smoking hull, an entirely different system of warfare had just been triggered. To understand why the German mathematical certainty of attrition failed so completely, we first need to examine why their own high command believed their superior heavy armor would win a war of exhaustion. The strategic reality facing German planners in the later years of the war was stark. They knew they could not win an industrial contest. At a range of 600 meters, the tungsten-cored projectile would strike the side armor of an American Sherman tank in less than 1 second. Against the sprawling factories of the American Midwest or the Soviet Urals. To compensate for a massive and growing numerical disadvantage, German military doctrine shifted sharply toward technological supremacy. The mathematics of attrition dictated that a numerically inferior force could only survive by inflicting drastically disproportionate casualties. If German industry could not build 5 tanks for every one they lost, they would engineer 1 tank capable of destroying 5. This desperate logic gave birth to the Panther and the Tiger. These were not merely combat vehicles, they were mobile fortresses designed to dictate the terms of any engagement, armed with high-velocity 75 and 88 millimeter guns. These heavy tanks could pierce American armor from 2,000 meters away, long before a Sherman could effectively return fire. The thick, sloped frontal steel of a Panther rendered it virtually immune to standard Allied anti-tank fire at typical combat ranges. To the officers in Berlin, these heavy fighting machines were the ultimate weapon against Allied volume. This reliance on superior machines generated a highly specific operational culture. German tank commanders were celebrated for their individual kill counts, and military propaganda lauded the armored aces who painted dozens of white victory rings on their long gun barrels. The resulting kinetic transfer was violent, definitive, and permanent. The gunner would see the bright flash of impact, hear the dull, heavy crack of fracturing steel. The institutional mindset became entirely fixated on the combat exchange rate. German intelligence officers calculated American shipping capacity, subtracted the daily battlefield claims submitted by their panzer divisions, and concluded that the Allied armored forces were slowly bleeding to death. The arithmetic seemed undeniable. A destroyed engine block was a permanently subtracted asset, but this calculation rested on a fatal, unexamined premise. German doctrine treated the battlefield as a final graveyard. When a panzer unit shattered an American armor column, leaving 20 immobilized hulls, in a muddy field, the German officers recorded 20 permanent kills. They assumed the Americans operated under the same rigid and unforgiving constraints that they did. For a retreating German army, a tank with a shattered drive sprocket or a blown transmission was a catastrophic, unrecoverable loss. If a machine could not move under its own power, it was dead metal. They believed this because of the very nature of the weapons they had built to win their war of attrition. In their singular pursuit of impenetrable armor and overwhelming firepower, German engineers had steadily pushed the weight of their combat vehicles far beyond the practical limits of standard battlefield recovery. A Panther weighed 45 tons, a Tiger weighed 56 tons, and watch the thick black smoke billow from the engine deck. The American crew would bail out into the grass. These were dimensions that defied the natural infrastructure of the European theater, crushing local bridges, destroying narrow village roads, and sinking deep into soft earth. The mathematics of attrition only worked if a broken tank remained a dead tank. The German High Command failed to ask what would happen if the enemy treated disabled machines not as corpses, but as wounded patients. Their kill claims were often physically accurate, but their definition of mechanical death was entirely wrong. The hidden flaw in their defensive strategy was not a lack of firepower, but a profound misunderstanding of logistics. To see why their assumption proved so disastrous, it is necessary to look closely at the sheer physical burden of their own armor, and what exactly happened the moment a 56-ton engineering marvel simply stopped moving. When a Tiger tank rolled to a halt in the deep mud of a contested European road, the sudden silence inside the fighting compartment was heavier than the armor. A shattered transmission or a snapped track pin did not just stop the vehicle. It transformed 56 tons of precision engineering into a static steel tomb. The crew would listen to the massive Maybach engine choke and die, breathing in the acrid smoke of burning clutch plates. In that moment, the most feared weapon in the German arsenal became a geographic obstacle. The machine was dead. By the evening of a sustained engagement, a competent German gun crew might count 3, 4, or even 5, that no local infantry commander knew how to solve. The fatal vulnerability of German heavy armor was hidden in its own blueprints. To mount the devastating 88mm gun and the thick plates of Krupp steel, engineers had accepted a Faustian bargain with physics. The sheer mass of the Panther and the Tiger put an agonizing, constant strain on their internal machinery. Gearboxes shattered under the torque required to pivot in soft soil. Final drives sheared apart, simply from the stress of moving the tank up a steep incline. These machines were so heavy they were constantly fighting the earth itself. This extreme mass required a radical solution for ground pressure. German designers implemented a complex system of overlapping and interleaved road wheels. It distributed the immense weight beautifully on a dry, paved surface. But on a battered, muddy battlefield, this engineering marvel became a mechanical curse. When mud, rocks, and debris packed between the densely layered metal discs and froze solid overnight, the tank literally locked itself in place. If an incoming anti-tank shell shattered a single inner road wheel, the crew could not simply swap it out. They had to spend hours unbolting and removing as many as 5 heavy outer wheels, just to reach the damaged part. They had to do this while jacking up a 56-ton behemoth in the mud, of these shattered green hulls smoking in a single field. According to the strict arithmetic of war, they had just erased an entire American armored platoon, often under the looming threat of indirect artillery fire. It was bespoke, artisan engineering applied to the brutal, abrasive reality of a mechanized war. Furthermore, German manufacturing often relied on minor custom adjustments during the production run. A mechanical component scavenged from one disabled heavy tank could not always be seamlessly dropped into the engine bay of another without careful machining by a skilled fitter. Every German heavy tank was a masterpiece of lethal capability, but they were built with the implicit assumption that the army would always be moving forward, controlling the ground on which it fought. When the strategic reality shifted and the German military was forced into a permanent, grinding retreat, the arithmetic of mass turned fatal. A broken tank can only be saved if the infantry lines hold long enough for specialized mechanics to do their work. If the front is collapsing, the machine must be towed out of the danger zone immediately. This is where the arrogance of the heavy armor program collided with absolute physical limits. The German military simply did not possess a standardized fleet of recovery vehicles capable of easily dragging 45 or 56 tons of dead weight across broken terrain. When the engine of a Panther or Tiger died in a ditch, the crew faced an impossible physics problem. The thick frontal armor that had protected them all afternoon was now the very anchor that doomed them. The German soldiers knew exactly how much steel, labor, and fuel it took to build a 30-ton fighting machine and ship it across an ocean. How do you pull a dead 56-ton steel fortress out of the mud under enemy fire? The standard heavy recovery vehicle of the German military was the SDKFZ 9 half-track, heavily relied upon and widely known as the FAMO. It was an impressive piece of machinery, powered by a massive 12-cylinder engine and designed to tow 18 tons. But a dead Tiger tank weighed 56 tons. The unyielding laws of friction, mud, and gravity dictated that pulling a disabled heavy tank out of a ditch required not one, but 3 of these prime movers, chained together in a staggered train. Picture the physical reality of this operation on a deteriorating dirt road in Normandy. 3 unarmored FAMOs are linked by thick steel cables, their heavy engines roaring, their drivers attempting to synchronize their gears and acceleration perfectly. If the lead driver engaged his clutch a fraction of a second too early, the sudden, immense tension could snap a heavy steel towing cable like a brittle wire, whipping it through the air with enough force to cut a man in half. If the mud was too deep, the tracks of the lead vehicles would simply spin and dig themselves deeper into the earth. It was a delicate, highly coordinated industrial operation that required flat ground, heavy lifting equipment, hours of daylight, and absolute safety from enemy artillery. They knew that replacing those losses would take weeks. That was the established rule of attrition. You kill the machine, and the enemy grows permanently weaker. By the late summer of 1944, the retreating German army rarely possessed any of those things. The desperate alternative was to use another operational Tiger or Panther to tow the disabled one. But this violated every mechanical manual issued to the crews. The transmission and final drives of a German heavy tank were already operating at the absolute limit of their engineering tolerance just to move their own armor. Forcing one to drag an additional tank 50-odd tons through soft soil almost invariably resulted in the towing tank shredding its own internal gears, instantly turning one immobile steel fortress into 2. As the sound of American artillery drew closer, the local German commander would face a brutal, inescapable choice. The recovery train was not coming. The tank could not be left intact for Allied intelligence to capture and evaluate. The crew, exhausted and covered in oil, had to reach for their demolition charges. The prescribed procedure was thorough. A thermite grenade was dropped into the open breech of the main gun, burning at over 2,000 degrees Celsius to melt the rifling and fuse the firing block into solid slag. Explosive charges were wired to the Maybach engine. The delicate, highly advanced radio equipment was shattered with sledgehammers. Finally, the crew would ignite the fuel lines. A machine that had consumed thousands of hours of skilled labor, scarce tungsten, and irreplaceable industrial capacity was reduced to a scorched iron carcass by the very men who had fought in it.